to Arup is, if you all agree, to keep his presentation to about 30 minutes, 35 minutes, and
Yeah,
then
sure.
the rest of the time for our question answer. I have a hard stop at 3, and I think many of you might have a hard stop as well.
I have a hard stop at 3.
Right. So let's try to do it. Arup, 30 minutes is good. We can have questions. So with that, it's over to you.
Yeah, sure. I will finish the stuff by 30 minutes. So, Professor Fox, could you please enable the sharing? Oh, okay.
I'm sorry. No, that's fine.
Okay, let me, Professor Fox, could you please enable the sharing? Because I'm unable to share my screen.
How about that?
Yeah, it is working perfectly. Are you seeing my screen?
Yes.
Okay. Professor Sullivan, you probably need to mute. Yeah. Okay. Thank you. Okay. Hey everyone. Today I will defend my qualification exam proposal. I proposed a heterogeneous data computing pipeline for scientific computing. I call it Radical-Cylon. My name is Arup Sarkar, and thank you for joining this presentation. So one of the main objective and motivation is in recent time, the exponential growth of data volume and the complexity is creating unprecedented challenges. In addition, the rise of the deep learning will expand USA market to 594 billions by 2032, which is more than 500% with a compound annual growth rate of 19.1%. Moreover, the global big data and data engineering market is doubled within 5 years, an astonishing 17.6% of a compound annual growth rate from 2022 to 2023. And apart from this huge growth rate, there is an interesting survey conducted by Anaconda indicates that a considerable amount of developer times is basically dedicated to the tasks like data pre-processing, data prototyping, and explorations. That data will be needed for the deep learning tasks or machine learning tasks, which is 33%. So from the scientific point of view, 33% of the developer exactly. From the research point of view, a massive investment in clouds and relevant frameworks solve new problems, obviously primarily due to the, again, big data revolutions and advancement in machine learning or of deep learning algorithms. And the total computing power in the world has quadrupled due to the AI engine deployment. Now, though data processing is a vital element in data engineering and deep learning pipelines, it often poses bottleneck in numerous applications. In addition, the presence of heterogeneity, high dimensionality, and the intricate relationships between variables make it difficult to process the data by using conventional analysis tool. So I'm seeing some. Okay, I'm seeing a floating menu here. So let me hide it so that you guys can see that. Okay, perfect. So yeah, so we can say that it is imperative to enhance the efficiency and scalability of data processing. And in addition, data science community is in the mode of transformations, moving away from the traditional use of SQLs and other tools and leaning towards the script-based programming style. Scripting-based programming style, no SQL, because SQL needs to query and it takes a big processing power of querying data. So rather than moving to the script-based programming style like Pythons to basically supports NoSQL databases and other tools to process this big volume of data. In addition, there are big companies, they provide the APIs in Pythons of machine learning or deep learnings that helps the developers to implement, to solve their problem into their domain. And here, obviously, data frame plays a central role, because ultimately these programming outputs data frames, and obviously, particularly in the Python ecosystem, thanks to libraries like pandas. And modern application has to deal massive data sets, often terabyte in range, and there is a limitation of processing this massive data in a single machine, even in the cluster node. So what could be the possible solution? Obviously, by using an efficient distributed data frame, and because it handles and processes large data volume by segregated all the data set into multiple machines and nodes with efficient resource management and schedule. So this basically addresses the scalability needs of today's data intensive application. So there are some priorities to solve this. Yeah, sure, Professor. You need to turn on the microphone.
Okay. Thank you. Oops. I think you need to. Can you turn off your speaker? Okay. Well, there's still an echo. I don't know how to make this work. Testing. Testing. Can everybody hear me? Thank you. Okay. So the title of this slide is Objective and Motivation. So what's the objective?
Objective is
Well, hang on. I mean, is it on the slide?
Yes.
Okay. What's the research objective?
Research objective to solve the problem of handling big amount of data into multiple clusters of knowledge. So that was one of the big objectives that will solve the current problem that presents the different state of our system.
Okay. I see. Okay.
So you will see all the steps.
Okay. Okay. The next time you give this talk, I think you want to look at the bullets on this slide and ask if any of them state the objective. I don't see the statement of an objective on this slide. Okay. So anyway, yeah, continue on. And I think it's going to come out as we go along. Good. I am turning off my microphone.
So thank you, Professor Sullivan, for the feedback. So I will definitely keep in mind. And is everyone hearing my voice? Hello?
Yes, we can hear you.
Oh, okay. Probably I have to. Oh. I have to enable the, sorry, audio settings here. Okay, sorry. Because I'm not hearing their voice, so I have to change the audio settings. Okay. Can anyone?
Hello.
Okay, yeah. Now I'm hearing. Okay, perfect. Thank you. Okay, so there are some priorities to solve these problems, like C++, like Cylon, which is a high-performance C++ kernel and distributed runtime designed for operator parallelism. It operates on a distributed memory data frames using bulk synchronous parallel patterns. And Cylon allows a single program multiple data computing pattern that utilizes Apache Arrow columnar data format for efficient data processing. The key structures are data frames, columns, scalar that are organized in a modular and layered architectures. And modules like, distributed data frame operator and communicator operators offer flexibility, allowing components such as communicators can be easily replaced by other communication libraries. If you see in these layer diagrams, you see that Cylon supports wide range of hardwares along with different transport layers that has TCP and infinity band, and most importantly, the communication layers has the support of different communication libraries like MPI and glues. And this can be, that MPI can be easily replaced by other communication frameworks. On the other hand, Pathway can handle infrastructure. Pathways gives a point. Pathway points a way to the direction of high performance computing. It also provides a sophisticated execution environment for deploying tasks. It also supports gang scheduling and parallel asynchronous dispatch for efficient resource management with conflict resolution on independent resources and output sharing. Here you see that there are different blocks, A, B, C. These blocks are they call basically island, and this island is nothing but a set of nodes that are used to process a specific task in one pipeline. So if there is a dependency of one task to other of the outputs, it can be easily resolved by the gang scheduling and parallel asynchronous dispatch. However, Pathways is a closed source and only compatible with Google Core infrastructures, and we don't have any idea how their distributed runtime environment works. And obviously, Pathway is not compatible with Cylon as well as you cannot use any loosely coupled communication libraries like MPI, UCX in Pathways.
Arup, Cylon is an open source system, and
yes, yes, Professor Mart.
Yeah, so Cylon is open source, Pathway is not open source.
Yes, Professor Marte, that's true.
Cylon is developed by Jeff's group here.
Scilop is developed by our team as well. We have started this project in 2020, at the beginning of the 2020, to basically propose a high performance computing, but Cylon do have some limitations. We will come into that later in the research problem section. So there are some other priors like Dask and Spark data frame that is also open source that can be an alternative to Cylon, but Cylon outperforms both in the multiple scaling operations. Whereas Rapid ScuDF is highly optimized for NVIDIA GPUs. We do have GPU Cylon, which is in the pipeline for scaling operations, but in this, Radical-Cylon is also the proposed framework is also support the GPUs as well. But for this qualification defense purpose, I tested these proposed frameworks on CPUs. I will share you why I have tested on CPUs. So in addition, Ray, which is another framework, provides distributed runtime that can be alternative of Radical Pilot. However, Ray is designed specifically to handle reinforcement job and is not compatible with wide range of SPC clusters like Cylon or Radical Pilot. We have made it compatible on Summits, on Rivana, even on UVSCS clusters, where Ray doesn't have any supports in these clusters. And actually, Ray is not tailored for distributed data processing, in fact, because Ray doesn't has any built-in primitives for partition data. Although this project recently introduced a Ray partition Ray dataset, but which is very primitive and based on the pandas. And in addition, in Ray, GPU support is restricted to scheduling and reservations. You cannot use GPUs with Ray. If you want to use, you have to rely on remote functions like, for example, TensorFlow, PyTorch. If you want to perform any machine learning jobs, you have to rely on that. And that TensorFlow and PyTorch has to handle all the workflow management. So which has the complexities by for using Ray. So here's a research problem. We understand that the priorities faces limitation for solving challenges of multiple data pipeline execution. And one side, Cylon requires underlying execution environment because it operates because its operations are performed sequentially as executables, and also supports single program multiple data. That hinders the compatibility of heterogeneous execution. I mean, Cylon requires. I told Cylon requires. So for instance, like in Cylon, if you want to perform join in one pipeline and sorting or machine learning in another pipeline, you cannot do that with the common hardware resources. So the need for underlying a task-based execution environment is apparent. Now, moreover, Cylon resource management is predetermined. You have to rely on Slurm-based allocations. You have to use Slurm or LSF, script for allocating resources, and resulting in idle resources when one worker finishes task that prevents the use of other pipeline in runtime. On the other side, obviously, Pathway doesn't support Cylon and heterogeneous cross-platform communications and data frame libraries. So the hypothesis is, yeah, sure. You need to enable.
Okay. If you just turn off your speaker for just a second, will be good. Turn down your volume.
I am turning down the volume.
Great. Can you turn off your speaker?
I'm trying.
No, the speaker on your laptop. Just mute your speaker. Oh, it's.
I think they can hear it.
I just hear an echo. It's not that. I think it's just the speaker on your laptop.
As Zoom is using, so that's right.
Yeah. Okay, great. Can you go back to the previous slide? Yeah, and can you move that Zoom bar so I can see the slide? Can you tell us a little bit more about the first bullet? How much does Cylon outperform these methods? And is that really the only problem with these methods? Is it just a performance difference? Is there something more fundamental there? And what I'm trying to understand is, whether you're proposing a mere kind of engineering improvement on, the performance of some existing software, or is there something fundamentally novel in your work relative to Dask and Spark data frame?
That Cylon outperformed Dask and data frames based on the execution, because Cylon uses different patterns, execution patterns. It uses box and parallel patterns. It takes all the data in a different way that Dask.
Okay. Right. Okay.
That execution pattern basically outperformed the Dask.
I see. Okay. Okay. So Cylon's already better than. Okay. Okay. So really you're addressing some shortcomings in Cylon here at the end of the day. Okay. All right. Thank you.
So the hypothesis is, if Radical-Cylon adopts a more flexible and heterogeneous execution model that allows simultaneous execution of multiple data pipelines with different operations, and integrates the dynamic task-based execution environment rather than relying on predetermined resource management,
Arif, we can't hear you. You need to connect your mic.
Okay. Sorry.
Okay, I think that would be good. Yeah, sure. So the hypothesis is if Radical-Cylon adopts a more flexible and heterogeneous execution model that allows simultaneous execution of multiple data pipeline with different operations and integrates a dynamic task-based execution environment rather than relying on predetermined resource management like SOM-based allocations, then we can say that it has the potential to overcome the current limitation. And with that, Radical-Cylon could enhance the efficiencies by minimizing the idle resources and improving compatibility with diverse data processing requirements in a distributed computing environment. So here we propose Radical-Cylon. It's a task-based environment for Cylon, where tasks are executed as radical functions. Comprise the different modules. Like you see in the pictures, there are 4 different modules, like pilot manager, task manager, MongoDB database, and remote agents. So these resources are allocated for here with this design. You see that both pilot managers and task managers basically uses resources like login node or compute node, and resources are allocated to multiple tasks, controlled by Radical-Cylon scheduler here, and that uses executor to perform the execution of the single program multiple data task. So this design allow efficient scheduling, placement, and launching of independent tasks across various compute nodes, enabling the execution of single, join, or sort operation, or probably scalar or other supported operation. There are 40 different supported operation into multiple pipeline at the same time. So if we put the Cylon, if you see in this picture, if you put the Cylon inside the design, we see that Cylon tasks are considered as the radical functions. This Cylon task can be the MPI task, can be the UCX task, can be the glue task. And here the pilot manager is basically responsible for allocated the resource. When the resource and task are there, then it will go to the remote agents, and remote agent basically create a new scheduler objects with the executor, and that will perform the underlying task into the CPUs or GPUs. You see the design support GPUs here. And the underlying idea, the basic underlying idea is the use of HPC optimizations like UCC, UCX, or MPI or glue, and arrow parquet can be combined over deep learning job, and the data pre or post processing can be implemented by reusing Radical Pilot for workflow. And here Cylon can be used as a high performance data frame to provide the data to the underlying deep learning pipeline. So here we are seeing that a bird's eye view of Radical-Cylon systems. A client program can be a multi-program, multiple data, and when a client evokes that task, then task manager will see that okay, we have multiple tasks here, along with the requested resources. The pilot manager will allocate it that resources from the system, and also send to the remote agent. The remote agent will see that how many tasks we have and how many resources are allocated. Then based on that, remote agents will create multiple data pipeline with dedicated schedulers and executor. Then a scheduler will schedule multiple tasks, and executor will basically perform each single program multiple data task that combines the multiple program multiple data here. So to prove this design, I have set up some experiments, and sorry, you see that there will be 3 main experiments, scaling experiments, and 1 overhead.
I have a question for you. I have a question. I have a quick question for you.
Yes, Professor Madhu, please. Yeah? Sure.
The question is, are you starting to tell us about your work now? Are you moved on from background and motivation to your work?
Motivation and these are the proposed design.
Right, but the experiments, this experimental slide is a first slide.
That is Arab's work.
That's my work.
Right. So your work, but you're transitioning now to your work, right? What you did for the exam. Is that correct?
Yeah. What I did in the experiment section. Yeah,
Right,
exactly.
right. My point is, it might be useful. I don't think you have a slide, but I think we discussed this before. It would be useful, ideally, to state precisely before we start to your contribution, what your questions were exactly, and what you achieved in it as in a summary manner, and then go to this part, because otherwise it's not very clear where that part ends, Arup, and where your work starts, right? I mean, ideally, and I don't think we can change anything right now, but if my colleagues agree, that would be a good thing to do. Say, in my exam, I propose the following 3 questions. Here is the rough my contribution, and now I go into this. That would be a good thing to have, because I sort of don't see that clear demarcation otherwise.
Okay. Thank you for this comment, Professor Marte. I was about to tell, what my contribution will achieve this, but I'm really sorry that we probably should have a separate slides to specifically mention that the contributions versus the experiments.
Right, contribution, and more importantly, we had agreed when we did the first part of the exam, we had agreed on some questions that you're going to work on, and we just want to understand. And you can change the question, but we just want to understand, are the same questions? Is it changed, not changed? Right? I don't sort of have a sense for that part, Arup, is all I'm saying. Right? This exam is response to the first part of your proposal, which you proposed a certain set of tasks. And you are welcome to change it, absolutely. In fact, that happens. Just don't have an understanding of how it connects.
This is basically the proposed system we have proposed here, and to implement that proposed system, these are the experiment, and what we'll achieve with that experiment is we have to perform the baseline experiments and as well as the proposed system experiment and compare that. So that's what exactly, we have to perform. We are proposing, heterogeneous execution pipeline, right? Multiple operations will be executed at the same time. So that's what I have said in the previous slides. So here we will see that whether our experiment will will achieve that objective or not, performing the join operations or sort operations in single pipelines or heterogeneous pipeline.
Right. So looks like one of the contribution of your exam is to carry out these experiments and analyze the data to understand whether the Radical-Cylon, not radical pilot, but radical.
Yeah, exactly.
Right? But that's a contribution. The second what is not clear to me is building parts of Radical-Cylon also part of this exam, or that's not part of this part of the exam. Maybe it is, maybe it's not. I do not know that.
It is building radical pilot is also part of the exam. So there are multiple exams here. So and I will tell what is the purpose of this experiment and how of this exam, and how that exam will basically support my proposal, and how Radical-Cylon is performing in different settings.
Okay, can go ahead. Am I the only one, Kevin, Jeff, and you, that is, maybe I'm causing more, but it's just not clear to me.
It's totally fine, Professor Marte. And this kind of question helps others to basically clarify a lot of things.
Yeah,
Okay.
I think my comment's consistent with what was just said. You run an experiment to test a hypothesis or to
exactly
run to measure a quantity.
I perform experiments to basically measure the hypothesis and see how proposed Radical-Cylon overcomes the existing problem.
Right. So in a kind of a rigorous experimental setting, you would set out some hypotheses first. You know, for example, a hypothesis about the relative scaling for join and sort. How much better do you expect Radical-Cylon to do than what baseline?
What is X? Right.
And then an experiment tests that hypothesis.
That's-
Or you could ask a research question, you know, what is the extent of improvement in scaling relative to some other technology? So I think what the question is that I'm hearing is, you know, what are the specific hypotheses? If you go back to your hypothesis slide.
Okay. So main target is to
See, this
achieve.
is so potential to overcome current limitations.
Yeah,
That's a
exactly.
good idea, but it's not very, and I hate to sort of, you know, push on the notion of quantification, but that could mean almost anything. Overcome by how much? In what dimensions? So be more precise really about what the specific hypothesis is. If I do the following, if I build the following thing, then I hypothesize I'll see the following improvements.
That is yeah, that's kind of explanation is there in each experiment slide. So I will
Okay,
all
all right. So
yeah,
let's go
okay.
look at those then.
Yeah,
Thank you.
okay, sure.
And I'm turning off my microphone.
Okay, so let me explain the experiment here first and what this experiment will do. So here you see there are three different scaling experiment. One is join, weak, and WS means weak, and SS means strong scaling. And also heterogeneous is you know, weak scaling and strong scaling. And I have performed these experiments on Rivana and also Summit. In Rivana, I have used 4 to 14 nodes in parallel, and on Summit node, I have used 2 to 64 nodes. And for 35 million, yeah, for weak scaling, I have used 35 million rows, and for strong scaling, I have used 3.5 billion rows. And Rivana supports, you know, 37 cores per node, and also Summit supports 42 cores per node. But for heterogeneous strong and weak scaling, what I did is our proposal is to you know, to see the performance of heterogeneous executions, like, you know, multiple you know, multiple tasks will be executed at the same times by using the allocated resource and see how it performs. So and obviously, as we are proposing one a system, we have to calculate the overheads as well. So, you know, if that that system overheads, you know, heavily, then we don't need to use that system, right? So these are the 4 different you know, experiment I have used. And here you see this is the scaling results on Rivana. What we are doing is the main target is to achieve the Radical-Cylon performance as bare metal Cylon in a single pipeline, because bare metal Cylon is using single pipeline, right? So as we are introducing a new system, we have to achieve similar performance as bare metal Cylon. So this is the first task, and see how the overheads goes. Then we will see, like, you know, how the heterogeneous execution basically improves the performance. And here in these graphs, you are seeing that for the weak scaling, 35 million rows will be used to ease parallelism. So ease parallelism is basically you know, aligned with the rank. So as in Rivana, there are 37 cores per node. So for 4 nodes, it will be 148 cores. So 148 cores will be assigned to 148 ranks. So that 148 ranks will be used at 148 parallelism here. So when 35 million rows is used, so that means one rank will use 35 million rows. So 35 million into 148. This will be the total number of rows in one table, in the global table. So and obviously, when the number of nodes increases, then there will be a all gather operation from all the ranks, and this communication will add additional overhead in both bare metal Cylon and in both Radical-Cylon. That's why you see the weak scaling. We are seeing a little bit of increasing time when the number of rank is increased. On the other hand, the strong scaling, here the process is different. Like 3.5 billion rows will be divided into 148 ranks, for example, for the fastest. So when the number of parallelism increases, then each parallelism will get less amount of rows, right? So that's why the expected behavior is, when the number of rank is increases, we will see less execution times. So we are seeing that for a single executions, both bare metal Cylon and Radical-Cylon is performing the same way. Even for short weak scaling, we are seeing that the Radical-Cylon is performing a little bit better. So let's see about the overheads of these experiments. And you are seeing that in the table that I have added overheads and as well as the execution times. And we are seeing that even the number of rank increases, overhead is not increasing that much. The overhead is calculated basically when the task is assigned, then it has to be deserialized to the task objects, and that task object has to construct an MPI combinator with n ranks. N ranks means 148 ranks or 518 ranks, and it has to deliver the task to all communicators. So that are the overheads basically, and we are seeing that for even the increasing of parallelism, we are not seeing the increasing of overheads. So that means overheads is constant. So when you use big tasks, then it will not increase the overhead.
So this overhead, is this overhead causing the performance difference between Radical-Cylon and bare metal? Because as you can see from the last slide, seems like weak scaling Radical-Cylon performs slightly worse than bare metal Cylon, right?
Yes, exactly. This overhead is adding that additional execution times. But if you see, each test is run 10 times, and this is the total times. 10 iteration is test. Like with the 4 nodes, 148 ranks, it run 10 times. So we have added the error bar here, and that error bar is basically overlapping. Because of that additional overlap, the execution type increases a bit. But on average, as error bar is overlapping, so we can say that Radical-Cylon is achieving similar performance as bare metal Cylon in single executions, single pipeline. Did my answer solves your question, Professor Cheng?
Yes. So I have a follow-up question. So how do these results connect to the objective and the motivation of that you presented earlier?
Yeah, that's a very good question. So you see, this experiment is basically execution of a single pipeline. Okay, so but when we use multiple pipeline and with multiple tasks at the same times, as this overhead is very minimal and constant, so it will not have impact on multiple tasks, and multiple tasks will execute very fast rather than the batch processing. So you will see that even with the multiple tasks, even with that overhead, Radical-Cylon is performing better.
So how do you provide, for example, resource isolation and performance isolation for multiple tasks that could be possibly executing at the same time using the same resources?
So here we are using a partial framework for master and worker architecture. So master have all the resources informations, and worker is performing all those, local sort, and then, all gather all this results. So when one worker, finishes his job, so master has the information. So master releases that resource, and that resource will be, scheduled by other pipeline workers.
Okay, so you are using parcel as a task scheduler, right?
Yeah, exactly.
Okay. Okay.
So the same experiment I have performed on Wardell Summit. This National Laboratory Summit National Laboratory cluster provides over 10,000 CPUs. You can run this scaling of operations, and its node has 42 cores, which is very big. And in this experiment, we have used 2,688 CPUs for multiple experiments. I will say why we have used that in the later. And we are seeing that for strong scaling, Radical-Cylon is achieving the same performance as bare metal Cylon. And for weak scaling, sort Radical-Cylon is performing a bit bad when the number of node is less, but ultimately it achieves it achieves the similar performance as bare metal Cylon when the number of ranks is increased here. And on the strong scaling side, you might ask a question like why the number of tasks is execution time is increasing when the number of node is increasing here. The main reason is if the number of the volume of the task is very less, like 3.5 billion is divided into a lot of cores, then a rank is not have that much of tasks. So because of that overhead, both bare metal Cylon and Radical-Cylon is taking a bit more time. So if we use, let's say, for like 10 billion rows, then we can see that this is scaling perfectly good. And so this is the one of the main important experiment graph we are seeing. The primary objective to see whether the task-based execution is performing okay or not, whether we are getting the same behavior of a scaling operation or not. So here we used 4 different tasks here. Initially, what I did, I use one task and running 4 times and see whether it is performing okay or not. And after achieving this, then I have used 4 different tasks like sort, join, weak, and strong scaling, and see whether we are getting the same behavior or not, like weak scaling behavior or a strong scaling behavior. And I have used the same configurations like 35 million for weak scaling and 3.5 billion for a strong scaling. And you are seeing that I am using 84 ranks, from 84 ranks to 2,688 ranks for different with 10 iteration each experiments. And we are seeing that scaling behavior is performing as it is. And one pipeline doesn't impact on other pipeline execution times. And we are seeing the graph for weak scaling. It is taking a bit more time when the number of rank increases, and for strong scaling, it is reducing the execution time. And in the next experiment, this is the most important experiment. How heterogeneous execution that we have used in Radical-Cylon is performing better than the batch processing of Cylon bare metal Cylon. So here we did is first 2 graph. One is for a strong scaling and another is for weak scaling. So a strong scaling, we have used 2 operations. One is join and sort at the same pipeline. There are 2 operations in the same pipeline. And for batch scalings, what I did is basically use these 2 operations, basic bare metal Cylon operation at the same times. And I have used same configurations, and each operation is basically running 10 times. And we are seeing that Radical-Cylon is performing better than bare metal batch execution Cylon, and which is in different configuration, it is achieving 4 to 15% of performance improvement despite of constant overhead. So in the bar graph, we are seeing that when the number of when the number of rank is increased, it is decreasing the performance improvement. It is because the task size is less. If we increase the task size, it will the execution time will be reduced more, and the performance improvement will be more. So despite of this amazing performance, Radical-Cylon has some limitation, and I set some plans to overcome it as a future work. The first limitation is like Radical-Cylon doesn't have any problem on Grafana and UVSCS cluster, but it is having some issues when I am using number of ranks is 2006 more than 2,688, and there are some issues I have created in Oak Ridge National Laboratory Summit clusters, and this is going back and forth with multiple teams, even teams who are working on Parcel, and as well as the Summit team, and hopefully we can fix that issue, because we are facing hard time for allocating the resources. And also design support GPUs, but there are some dependencies of CUDA or MPI and CUDF with the system, like on Grafana and Summit, and which is will take a bit more time to stable, and we need back and forth communication with those system admin. And also we do have a plan to perform experiments on CPUs and GPUs at the same times. And for deep learning job, a separate process is needed because the Cylon provides output data frames, and that will be used as a input for deep learning jobs. And we do have planned to support a seamless executions of machine learning, including deep learning jobs with Cylon data frames. So that will be my next task. And obviously there are some, as we have used Arrow, and Arrow depends on a query engines that will be used to query data, and we do have some plans to improve the Arrow engine as well. So in conclusion, the future of the proposed design is achieved the cutting-edge multi-execution paradigm in today's data engineering and machine learning execution landscape, which predominantly employs SPMD approaches. So this compatibility extends to multi-execution setups using Slurm or SRun on top of Cylon. The proposed design tackles the intricacies of resource management and resource management and the execution of diverse data pipeline with the 4 to 15% improvement of execution time. This transformation includes an efficient resource management and scheduling framework that interfaces between client and cluster node. And the outcome of this unified model enhances user access to more comprehensive computing pattern. So these are some references I have used, although there are more references are there in the report. This is all my presentation. Thank you for joining. If you have any questions. Conclusion? Oh, okay. I will read. Okay. Okay, sure. Basically we are proposing Radical-Cylon that will achieve a cutting-edge multi-execution paradigm for data engineering or ML execution landscape, and with the combination of single program multiple data execution that will employ the multiple program multiple data, which will utilize the resources efficiently. And also we are using Slurm or SRun multi-execution setup with Slurm SRun based on the cluster, and obviously it will tackle some complexities of resource management and scheduling, and it has the improvement of 4 to 15% based on the configurations. And obviously, but this will help as we have planned to support on multiple supercomputers and give a sophisticated portal for users. So basically, this will help.
Thank you. Multiple of us have hard stops in 5 minutes, so that's just a time check here.
Okay.
Right, so let's go around and maybe you want to start first, given that me and Kevin spoke more during the meeting, and then we can go to Kevin, then myself and Jeff. And
Okay, so so it sounds like your proposal is about to design a one-size-fits-all framework that combines data engineering, data processing, and machine learning model training, correct?
And inferencing as well. Yeah.
Yeah, but my question is, why, given the existence of existing deep learning frameworks, for example, PyTorch and some other tools for inference, for hosting models, so why not directly using them and basically just glue Cylon or Radical-Cylon with PyTorch so that you really focus on the best you could do and you use other frameworks and take advantage of that, because that's what, for example, PyTorch is best at supporting.
The main reason is that, we have a data source from diverse, data type. And in the first slide, in the motivation page, I have said that, 45% of the developer times are basically used to pre-process the data. And there are also other sources of survey which, significant amount of that task is basically wasted because we are not preparing data efficiently. And if we think about a total pipeline, data processing, and also machine learning, but in the current study, if we use PyTorch or TensorFlow, then we have to rely on the workflow system to that specific clusters. That one problem, and as well as, we should have some prepared data in hand to give PyTorch or TensorFlow for training or inferencing. So the question, the suggestion you just said that, in fact, that will be my next task, seemingly, seamlessly utilize Cylon data frame as a input of the PyTorch or TensorFlow, and reduce. Yeah, sure. Yeah. Yeah, sure. So that's that's all, Professor Cheng. Is that answer your question?
Well, partly, but given the time limit, Kevin, you want to go next?
Can we one?
No, I'm also.
Okay. So is there any other question, Professor Marte?
so I'll yield. I have quite a few questions, but I'll yield for now because I think we need to spend some time talking amongst ourselves for 5 minutes at least to get a general sense. So my suggestion to you, Arup, is Jeff the host of this meeting?
Yes, Professor Fox.
So first of all, can we stop recording? It's a good time to stop recording.